In mathematics, matrix multiplication is a binary operation that takes a pair of matrices and produces another matrix. Numbers such as the real or complex numbers can be multiplied according to elementary arithmetic. On the other hand, matrices are arrays of numbers, so there is no unique way to define the multiplication of matrices. As such, in general the term matrix multiplication refers to a number of different ways to multiply matrices. The key features of any matrix multiplication include the number of rows and columns the original matrices have, and specifying how the entries of the matrices generate the new matrix. Like vectors, matrices of any size can be multiplied by scalars, which amounts to multiplying every entry of the matrix by the same number, similar to the entry-wise definition of adding or subtracting matrices. Multiplication of two matrices of the same size can be defined by multiplying the corresponding entries, and this is known as the Hadamard product. Another definition is the Kronecker product of two matrices. To obtain a block matrix, one can form many other definitions. However, the most useful definition can be motivated by linear equations and linear transformations on vectors, which have numerous applications in applied mathematics, physics, and engineering. This definition is often called the matrix product. In words, if A is an n times m matrix and B is an m times p matrix, their matrix product AB is an n times p matrix, in which the m entries across the rows of A are multiplied with the m entries down the columns of B. This definition is not commutative, although it still retains the associative property and is distributive over entry-wise addition of matrices. The identity element of the matrix product is the identity matrix, and a square matrix may have an inverse matrix. Determinant multiplicativity applies to the matrix product. The matrix product is an important operation in linear transformations, matrix groups, and the theory of group representations and IRIPs. Computing matrix products is both a central operation in many numerical algorithms and potentially time-consuming, making it one of the most well-studied problems in numerical computing. Various algorithms have been devised for computing C=AB, especially for large matrices. This article will use the following notational conventions. Matrices are represented by capital letters in bold, e.g., A, vectors in lowercase bold, e.g., A, and entries of vectors and matrices are italic, e.g., A and A. Index notation is often the clearest way to express definitions, and is used as standard in the literature. The ij entry of matrix A is indicated by ij or aij, whereas a numerical label on a collection of matrices is subscripted only, e.g., A1, A2, etc. Scalar multiplication. The simplest form of multiplication associated with matrices is scalar multiplication, which is a special case of the Kronecker product. The left scalar multiplication of a matrix A with a scalar lambda gives another matrix lambda A of the same size as A. The entries of lambda A are defined by explicitly. Similarly, the right scalar multiplication of a matrix A with a scalar lambda is defined to be explicitly. When the underlying ring is commutative, for example, the real or complex number field, these two multiplications are the same, and are simply called scalar multiplication. However, for matrices over a more general ring that are not commutative, such as the quaternions, they may not be equal. For a real scalar and matrix, for quaternion scalars and matrices, where I, J, K are the quaternion units, the non-commutativity of quaternion multiplication prevents the transition of changing ij equals plus k to g equals minus k. Matrix product. Assume two matrices are to be multiplied. General definition of the matrix product: if A is an n times m matrix and B is an m times p matrix, the matrix product AB is defined to be the n times p matrix, where each ij entry is given by multiplying the entries aik by the entries bkj. for k equals 1, 2, m, and summing the results over k. Thus, the product AB is defined only if the number of columns in A is equal to the number of rows in B, in this case m. Each entry may be computed one at a time. Sometimes, the summation convention is used as it is understood to sum over the repeated index k. To prevent any ambiguity, this convention will not be used in the article. Usually the entries are numbers or expressions, but can even be matrices themselves. The matrix product can still be calculated exactly the same way. See below for details on how the matrix product can be calculated in terms of blocks taking the forms of rows and columns. Illustration: the figure to the right illustrates diagrammatically the product of two matrices A and B, showing how each intersection in the product matrix corresponds to a row of A and a column of B. The values at the intersections marked with circles are examples of matrix products: row vector and column vector if the matrix products are. And note AB and bar are two different matrices. The first is a 1 times 1 matrix, while the second is a 3 times 3 matrix. Such expressions occur for real-valued Euclidean vectors in Cartesian coordinates, displayed as row and column matrices, in which case AB is the matrix form of their dot product, while bar the matrix form of their dyadic or tensor product. Square matrix and column vector if the matrix product is. However, bar is not defined. The product of a square matrix multiplied by a column matrix arises naturally in linear algebra, for solving linear equations and representing linear transformations. By choosing A, B, C, P, Q, R, U, V, W in A appropriately, A can represent a variety of transformations such as rotations, scaling and reflections, shears, of a geometric shape in space. Square matrices if the matrix products are, and in this case, both products AB and bar are defined, and the entries show that AB and bar are not equal in general. Multiplying square matrices which represent linear transformations corresponds to the composite transformation. Row vector, square matrix, and column vector if the matrix product is. However, CBA is not defined. Note that A equals C. This is one of many general properties listed below. Expressions of the form ABC occur when calculating the inner products of two vectors displayed as row and column vectors in an arbitrary coordinate system, and the metric tensor in these coordinates written as the square matrix. Rectangular matrices if the matrix products are, and properties of the matrix product analogous to numbers. Matrices satisfy the following general properties, although there is one subtlety. Due to the nature of matrix multiplication, all matrices not commutative, in general, because AB and bar may not be simultaneously defined, and even if they may still not be equal. This is contrary to ordinary multiplication of numbers. To specify the ordering of matrix multiplication in words, pre-multiply A by B means bar, while post-multiply A by C means AC. As long as the entries of the matrix come from a ring that has an identity, and n greater than 1, there is a pair of n times n non-commuting matrices over the ring. A notable exception is that the identity matrix commutes with every square matrix. In index notation, distributive over matrix addition, left distributivity, right distributivity. In index notation, these are respectively. Scalar multiplication is compatible with matrix multiplication, and where lambda is a scalar, if the entries of the matrix are real or complex numbers, then all four quantities are equal. More generally, all four are equal if lambda belongs to the center of the ring of entries of the matrix, because in this case lambda x equals x lambda for all matrices x. In index notation, these are respectively transpose, where T denotes the transpose, the interchange of row I with column I in a matrix. This identity holds for any matrices over a commutative ring, but not for all rings in general. Note that A and B are reversed. In index notation, complex conjugate If A and B have complex entries, then where asterisk denotes the complex conjugate of a matrix. In index notation, conjugate transpose. If A and B have complex entries, then where denotes the conjugate transpose of a matrix. In index notation, traces. The trace of a product AB is independent of the order of A and B. In index notation, square matrices only identity element. If A is a square matrix, then where I is the identity matrix of the same order. Inverse matrix. If A is a square matrix, there may be an inverse matrix A-1 of A such that if this property holds, then A is an invertible matrix. If not, A is a singular matrix. Moreover, determinants. When a determinant of a matrix is defined, if A and B are square matrices of the same order, the determinant of their product AB equals the product of their determinants. Since det and det are elements of the said commutative ring, det equals det, and so det equals det, even when AB bar. Matrix product. Matrix multiplication can be extended to the case of more than two matrices, provided that for each sequential pair, their dimensions match. The product of n matrices A1, A2, and with size is S0 times S1, S1 times S2, Sn-1 times Sn, is the S0 times Sn matrix. In index notation, properties of the matrix product. The same properties will hold, as long as the ordering of matrices is not changed. Some of the previous properties for more than two matrices generalize as follows. Associative. The matrix product is associative if three matrices A, B, and C are respectively M times P, P times Q, and Q times R matrices. Then there are two ways of grouping them without changing their order, and is an M times R matrix. If four matrices A, B, C, and D are respectively M times P, P times Q, Q times R, and R times S matrices, then there are five ways of grouping them without changing their order, and is an M times S matrix. In general, the number of possible ways of grouping n matrices for multiplication is equal to the Th-Catalan number. Trace. The trace of a product of n matrices A1, A2, and is invariant under cyclic permutations of the matrices in the product. Determinant. For square matrices only, the determinant of the product is the product of determinants. Examples of chain multiplication similarity transformations involving similar matrices are matrix products of the three square matrices. In the form, where P is the similarity matrix and A and B are said to be similar if this relation holds. This product appears frequently in linear algebra in applications, such as diagonalizing square matrices and the equivalence between different matrix representations of the same linear operator. Operations derived from the matrix product. More operations on square matrices can be defined using the matrix product, such as powers and nth roots by repeated matrix products. The matrix exponential can be defined by a power series, the matrix logarithm is the inverse of matrix exponentiation, and so on. Powers of matrices. Square matrices can be multiplied by themselves repeatedly in the same way as ordinary numbers, because they always have the same number of rows and columns. This repeated multiplication can be described as a power of the matrix, a special case of the ordinary matrix product. On the contrary, rectangular matrices do not have the same number of rows and columns, so they can never be raised to a power. An n times n matrix A raised to a positive integer k is defined as, and the following identities hold, where lambda is a scalar, 0 power, where I is the identity matrix. This is parallel to the 0th power of any number which equals unity. Scalar multiplication. Determinant. The naive computation of matrix powers is to multiply k times the matrix A to the result, starting with the identity matrix just like the scalar case. This can be improved using exponentiation by squaring, a method commonly used for scalars. For diagonalizable matrices, an even better method is to use the eigenvalue decomposition of A. Another method based on the Cayley-Hamilton theorem finds an identity using the matrices characteristic polynomial, producing a more effective equation for A in which a scalar is raised to the required power, rather than an entire matrix. A special case is the power of a diagonal matrix. Since the product of diagonal matrices amounts to simply multiplying corresponding diagonal elements together, the power k of a diagonal matrix A will have entries raised to the power, explicitly, meaning it is easy to raise a diagonal matrix to a power. When raising an arbitrary matrix to a power, it is often helpful to exploit this property by diagonalizing the matrix first. Applications of the matrix product. Linear transformations. Matrices offer a concise way of representing linear transformations between vector spaces, and matrix multiplication corresponds to the composition of linear transformations. The matrix product of two matrices can be defined when their entries belong to the same ring, and hence can be added and multiplied. Let U, V, and W be vector spaces over the same field with given bases V, W and T. U, V be linear transformations and St. U, W be their composition. Suppose that A, B, and C are the matrices representing the transformations S, T, and St with respect to the given bases. Then A B equals C, that is, the matrix of the composition of linear transformations is the product of their matrices with respect to the given bases. Linear systems of equations. A system of linear equations with the same number of equations as variables can be solved by collecting the coefficients of the equations into a square matrix, then inverting the matrix equation. A similar procedure can be used to solve a system of linear differential equations. See also phase plane, group theory and representation theory. The inner and outer products. Given two column vectors A and B, the Euclidean inner product and outer product are the simplest special cases of the matrix product. Inner product. The inner product of two vectors in matrix form is equivalent to a column vector multiplied on the left by a row vector, where it denotes the transpose of A. The matrix product itself can be expressed in terms of inner product. Suppose that the first n times m matrix A is decomposed into its row vectors I, and the second m times p matrix B into its column vectors by, where then it is also possible to express a matrix product in terms of concatenations of products of matrices and row or column vectors. These decompositions are particularly useful for matrices that are envisioned as concatenations of particular types of row vectors or column vectors, e.g., orthogonal matrices and Markov matrices. Outer product. The outer product of two vectors in matrix form is equivalent to a row vector multiplied on the left by a column vector. An alternative method is to express the matrix product in terms of the outer product. The decomposition is done the other way around. The first matrix A is decomposed into column vectors I and the second matrix B into row vectors by, where this time this method emphasizes the effect of individual column-row pairs on the result, which is a useful point of view with e.g. covariance matrices, where each such pair corresponds to the effect of a single sample point.